as John would say, meet robots and laser skeletons part 2. Okay, so we know that when humans walk over more complex terrains like this, we direct our gaze to gather visual information about the upcoming terrain in order to guide foot placement. And this leads to a couple of important questions. First, what kinds of visual information support foot placement? And how does degraded visual information, like might be encountered with certain visual disorders, change the relationship between gaze and gait? So this project focuses on the role of binocular visual information. This is information that is the result of having two eyes with two slightly different pictures of the world. We expect it to be an important source of information for walking over complex terrains because binocular visual signals provide depth cues, and the problem of foot placement in complex terrains seems to be a geometric problem in which depth structure would be important information. So in this experiment, we measured eye movements and body motion during walking over complex terrain with normal binocular vision and degraded binocular vision, which we imposed by blurring the input to one eye using something called a Bangerter foil. This effectively makes a 20/20 eye into a 2100 eye, disrupting the visual system's ability to combine information across the two eyes. In our experiment, subjects walked about a half mile out and back on a trail. We pre-designated chunks of that trail, flat, medium, and rough. Here's a visualization of our data from a chunk of medium terrain. You see the person walking on the left, the world video on the right, and the eye traces below. Some people have told me it looks like the person is walking near like a crazy cliff, but that's actually a lake, so they're safe. It's all good. So the data is very rich, but today I'm just going to talk about two very simple measures. And these two measures are look-ahead distance and look-ahead time. At every instance in time, we find the closest point on the path to the gaze point at that time. Then we can measure the distance from the walker to that point in space, as well as how long it will take them to get there along the path. So following that procedure, at every point in the recording, we get distributions of look-ahead distance, as well as distributions of look-ahead time. And here are the look-ahead distance distributions for the three terrains in the binocular condition. Subjects look closer to their body in space as the terrain becomes more difficult. So the bottom curve here is the flat terrain, and then it goes from medium to rough. On the other hand, subjects exhibit a relatively constant look-ahead time of 1.5 to 2 seconds. Both of these results are consistent with previous work on complex terrains, and this is actually pretty cool because these are 8 completely different observers from John's original experiment on different terrain collected by a different researcher, and we collected on a continuous out and back hike instead of in short segments of the terrain separated. But we're here for the binocular vision, so let's compare to the binocular degraded condition. We'll focus on the medium and rough terrain where gaze is clearly coupled to gait. And now overlaid are the look-ahead distance distributions in the degraded condition. There's a shift for the medium terrain, which becomes more apparent if we look directly at the average difference across conditions, which I'm plotting here with these purple traces. So, in the medium terrain, subjects allocate their gaze closer to their body in space. And the same is true for look-ahead time. You'll notice that this isn't the case in the rough terrain. We think that this is because the difficulty of the task is swamping any difference between these two conditions. Finally, we also collected preliminary data in the same experiment for one additional group of observers. These subjects all had visual disorders which confer permanent deficits to binocular vision. These include things like amblyopia, which is colloquially called lazy eye. And these subjects who've had a lifetime to adapt to their deficits show an even larger shift toward the body in the medium terrain, both in distance and in time, and both in the medium, suggesting that perhaps there's something adaptive to shifting the gaze closer to the body. And in fact, if we take stereo acuity, which is a simple measure of binocular depth perception, binocular depth perception is actually an ability which does vary in the general population, even what we would consider to be corrected to normal vision. And if we do that and plot the median look-ahead distances and the median look-ahead times against that stereo acuity for all of our observers in their normal viewing conditions, we actually see a relationship between binocular function and gaze allocation during walking. So in conclusion, binocular cues seem to provide a source of visual information during walking. In particular, binocular deficits are associated with a gaze strategy that is shifted closer to the body. But what we don't yet know is if this shift in gaze strategy is a general response to increased visual uncertainty or is potentially driven by the size of the binocular cues and the availability of the monocular cues. I'd like to thank my collaborators, especially the folks at UC Berkeley who hosted us for this project and facilitated our work with clinical populations.
Questions? Let me start. So, couldn't quite get how walking speed relates to this.
Right, so the shifts that we see in gaze strategy are actually independent of walking speed. So if we measure walking, like the distribution of walking speeds across these different conditions, we do see a difference across the terrains, but not across the two conditions, like between when we degrade their visual information and when they're just walking normally.
How about people who are chronically like that? Do they walk slower?
Not that I remember, but I should check, yeah.
It's interesting that you can apply this perturbation to them and then not respond by walking slower.
Right, so people, it's interesting talking to subjects after this because, so when you first put on one of these Bangerter foils, I was sitting at my desk, I put on our little glasses piece, and I thought to myself, well, that didn't do anything. And then I reached out to try to grab my coffee cup and I missed. And so I think that a lot of vision is completely preserved. And so subjects would report feeling like a little bit uncomfortable, but they're still able to move through the world. And so I guess maybe it's a little bit surprising that we don't see a measurable difference in walking speed, but visual function is still there. You can still see pretty well.
James?
Based on what you just said, how you didn't perceive a difference, when you immediately put on the, I would call it a blinder, until you acted, did you see anything similar in the data where once people started, once they started walking, you saw more stumbles or anything along those lines?
I don't think.
You have to learn through action.
Right. I don't, from watching the videos, I didn't observe noticeably more stumbles. I mean, people are pretty good at walking over these types of hiking trails. It wasn't, and our rough terrain wasn't even as rough as John's was back in Austin. And so I didn't, and I'm usually after things that are more measurable. So I didn't notice more stumbles and I didn't try to quantify that either.
Art?
Now that you guys have totally revolutionized the field and moved outside the lab, I kind of want you to move into the lab.
Yeah, we feel the same way.
You could have fake terrain and manipulate different visual cues.
Yes, so we completely agree. This is very observational data and it opens up a lot of important questions, some of which we'll be able to answer because they're building these fancy new, both with VR and also there's these new projectors that allow you to project sort of ground planes onto the floor and manipulate visual cues that way. So we're excited to both be outside and also go back to the lab.
Could the next speaker come and get set up and mic'd up and so on?
So I'm wondering if you had only subjects wearing no glasses or if do you have some limitations there?
So our sort of corrected to normal observers all were wearing contacts if they had some prescription. In a longer talk, I might discuss what exactly their corrections were and what their corrected to normal vision looked like. But we measured that, but I can't sort of spew that off in a.
Because I'm wondering if this influences how well you can feel with the impairment or with the disturbed vision, because people wearing glasses are kind of used to have disturbances in their view. They just at home and put off the glasses and have to walk around. So I'm wondering if you can see a difference between healthy subjects and people which have already spectacles.
I'm not sure. So your question is if we were to look at the difference between people with and without their glasses on.
Yeah.
So
with people having glasses at all and totally healthy people. you kind of see a difference there.
If the person's vision is successfully corrected to normal, my guess is the difference would be immeasurable, especially in this kind of experiment. You wouldn't see a difference that we can measure.
Let's thank the speaker.